Yeah, good morning to everyone. So we heard warm words up to now. So we had the keynote session setting the scene, and I think we now have the global perspective. But now we make the deep dive, and we start with the energy production. We already heard, no, this is not really correct. We should name it conversion, but we want to talk about the renewables. And the renewables, we also decided in advance that we would like to focus on the challenges, and this is what we would like to show. What is the order? The order of speakers is slightly different as you see it within the paper here in front of you. We will start with Bernd Rech. He is already sitting over there. I ask the speakers always to go there. Thank you. And Bernd, he will start with a rough overview and then comes into the PV technology. And after that, we learned that we have to talk about fluctuation, and this is what Jay Abt will pick up. He will be the second one, and talking about the challenges of the fluctuations which we have with the renewables. Afterwards, we said, okay, now we have our fluctuation, and we go back and to Eva Schill, and she will talk about the geothermal power. So we could have steady state loading, we could have, but we also switch now over to heat and not electricity anymore. After we had that one, we have the final speaker, and this is Iris. And Iris will talk about the challenge of stability and sustainability. And we thought this is a good closing speak. And this is our order, and now Bernd Rech will start. I said he will speak about he will give some overview. But let me introduce Bernd Rech. Bernd Rech, he is a scientific director of Helmholtz Zentrum in Berlin, and he is also professor for photovoltaics at the Technical University of Berlin. His research interests comprise PV, renewable energy technologies, storage, solutions, and sustainable fuels. So he is the correct person, the right person for here. And he is also within the Helmholtz Association, the designated vice president in the research field of energy. So Bernd, it's your turn.
Jutta, thank you very much, and certainly, I don't know, do I need to share the, oh, okay, there it's already. Certainly, I also would like to start with a few words with Iris sitting now on the screen. We had some exchange about the situation, terrible situation in Israel. On Monday, we had a joint PhD defense with Leos Edgar, not joining us, but chairing the next session. So we really feel with our friends in Israel and are really terrified by the situation. Coming to the presentation, I would like to quickly step into the situation of power production in Germany. This was already introduced by Robert in his presentation. So it's a quite busy slide, but what you can see is that we have at the moment 500 terawatt hours electricity production in Germany. About 50% of it is renewable, so 250 terawatt, and still a significant fraction from biomass. If you look on the years ahead to come, we need to increase it dramatically. And the question is if we need to go to 1,000 terawatt hours due to additional electrification, or even more if we want to go to hydrogen, which means most of the increase needs to be driven by solar and wind, even in Germany. This means that we have to increase capacity by a factor of 4 or factor of 8 for renewables, and even larger since it's driven by wind and solar. So there are the German goals. We will have a strong increase at the moment, like in the EEA study. PV is strongly increasing. Wind is more difficult because there is more issues related to acceptance, as Robert said before, than let's say in the PV sector. But if you look ahead, many things have to be done. The good news about the fluctuations is, at least in Germany, if you look on the yearly distribution, so we have more sun in summer and more wind in winter in Germany, so it's on this level somehow balanced. However, as Robert shows, if we are going on a daily part, and it's getting let's say, more challenging. And Jay will talk about fluctuations in energy in his presentation, so to take up about this. For the part of PV, I would like to dig a bit deeper in solar cell technologies. And if you look about this from the fundamental principle, if you have a so-called single junction solar cell, like every PV module or almost every module you have now on the global market, which is a crystalline silicon-based solar cell, which has an theoretical efficiency potential of 30%. More is not possible, but with this semiconductor technology, the big boom of PV was driven over the past decades. So which means today we have more than 90% of all solar modules are based on crystalline silicon. They typically have an efficiency of around 20%. Maybe they will come up to 25% in the next years. All this is mainly driven by a very few countries, and about 90% of the, let's say, value chain is by production in China and Southeast Asia. So, but if you look on what is possible from a physical point of view, then you can use different semiconductor materials, make tandem solar cells, triple solar cells, so to put them on top of each other, and then you can increase efficiencies, potentials above 40%, about 50% using this. And if you look on the quantity what is needed, how PV is driving, certainly a factor of 2 higher efficiency would solve a lot of issues regarding the availability of areas. It would further reduce the costs because most of the costs are not anymore the solar cell itself, it's the mounting, it's all the infrastructure around. You would have significant less area use, less resources in principle, because most of the resources are glass, are cables, and this would also open new markets. So that's a driving force for new PV technologies. And one of the, let's say, most promising materials are so-called metal organic perovskite. So this is a new hybrid semiconductor, or rather new hybrid semiconductor, and it has the advantage that it can, in a first step, be a partner of crystalline silicon, so you can put it in addition to the mainstream technology as an add-on technology. And with this, you can go to so-called tandem solar cells, which have now shown to have efficiencies on small areas up to 33.7%. You can combine it also with other materials like thin film CIGS, or you can also think about a fully perovskite-based technology. And this I will put a bit at the end of the presentation. So there's a race for higher efficiencies, and this is at the moment a race in laboratories for this perovskite silicon tandem cells. I just highlighted a recent graph from the Renewable Energy Lab in the US, the NREL, which shows that this technology in the past years has step by steps increased in efficiency, and also our center could contribute some of these values. And I will briefly show as a scientific example what needs to be designed, and this brings maybe also some topics how this can be scaled up later on. It's also a very big international research topic, so where you can also look, for example, on the perovskite database, which now collects lots of results worldwide about this new material. So in principle, to see with this material, you can increase the efficiency up to or above 30%, so clearly above what is possible with silicon alone. But a lot of things have to be still to be developed to really get it scaled up. And the fascinating thing about this semiconductor material is that it's very different from, let's say, I'm a silicon guy, so I'm used to work with silicon over most of my career. But with this new type of material, you can have low temperature processing. You can, in principle, print the material, However, you need to print it on quite complicated structures like surface textures. You have to embed transport layers which are based on monomolecular films. So it's a physical topic, but there's also a lot of chemistry involved because it combines classical semiconductors, but also new chemistries and somehow new materials which were still in the design phase. So with this kind of materials you can do the high efficiencies. However, and now comes the next point, you have to do it, and it's demonstrated on square centimeters. It's not even really fully stable, so we will talk about this. Iris will pick up on it, and now it needs to be transferred on the so-called wafer size. You see it on the right-hand side, and then from one wafer to millions of wafers, how PV is working at the moment with high reliability. So this is let's say, a very big challenge. The other part is it would promise to find new materials to get rid of the silicon itself. So this is an example of a tandem solar cell which is solely based of two perovskite films with different band gaps which share the solar spectrum, what you see on the right side, which already also has a quite high efficiency. And the interesting part is if it's possible to really go to the number of junctions. This is one study showing the CO2 footprint for classical silicon solar cells on the left side. So the black one is the CO2 gram in CO2 emission per kilowatt hour. And the blue bar is the conversion efficiency. And if you go to more and more junctions, and on the right-hand side, it's an example of a 3-terminal solar cell, which has with an efficiency for the calculation of 35%, then you could gain a lot in the CO2 footprint and also have the advantage of the higher efficiency. And as mentioned, there is still a lot of research to be done. And what we see here in this kind of roadmap is the yellow roadmap is if we go on with the today's technology, which is proven, which is successful, which is scaled up and will be scaled up even stronger across the next decade. But from the efficiency side, going to tandem triple junctions, this would open up also a new path for PV and for certainly all what Robert needs later on, cheap electricity to do all the chemistry which is needed. And Iris will in her talk go then more on the stability and sustainability issues. Thank you very much.
So, and as mentioned before, now we come to the next presenter. It is Jay Abt, and he will talk about the fluctuations and the challenges coming together with those fluctuations. His talk is named Characteristics of Wind and Solar Power, now we have both, and their importance for grid integration. Who is Jay Abt? Jay Abt is an emeritus professor at Carnegie Mellon University, and there at the Tepper School of Business, but also in the Department of Engineering and Public Policy. He is a physicist by training and directed the Renewable Electricity Project at the university, and he co-directed the Carnegie Mellon Electricity Industry Center. So, long word. So, Jay, it's your turn.
Thank you very much. We all know that wind and solar power output is variable. What I want to try to do today is to tell you some of what we've learned about the basic physics and mathematics of those variable outputs and what that means for grid integration. So this is what one means by variability. This is 1 hour time resolution data of all of the wind in the US state of Texas, the largest wind installations in the state. And there is both hour-to-hour variability and seasonal variability. This is 2 years of data, so you can see the dips in the late summer and the rises in the spring. So the question is, how much of that fluctuation is at what time scales? That is, what is the amplitude at various frequencies of that? So we found that wind's variability is not white noise, right? White noise has the same amplitude at all frequencies. And wind's power output has much less high-frequency power than that. If wind had been white noise, it would have been impossibly expensive to integrate. It would have needed a lot of very fast adjusting power to compensate, but the fluctuations are 100 times larger at long periods, like an hour or a day, than they are at short periods like an hour or minutes. So that means that even slow ramping fossil plants can be used to compensate. And we don't need a great deal of very expensive capital resources that are not used very often. So let me tell you a little bit about the detailed character of that. And to do that, we want to Fourier transform the time domain output into frequencies, right? So you all have equalizers in your playback machines, and with the bass notes on the left and the treble notes on the right, and individual frequencies. So what I'm going to show you is the amplitude of wind power at these various frequencies. So here is that spectrum. Again, the bass notes on the left, the treble notes on the right, and this is 1 second wind data over a bit more than 2 months. And there's a lot of interesting features about this graph, but I want to draw your attention in this brief talk to this straight line that falls off as frequency to the -5/3, remarkable behavior over 4 orders of magnitude of frequency. And from that, we can learn a great deal. The theorists, Golan Bell in Israel and Mahesh Bandi in Japan, have shown that the turbine spectrum can be explained by what's called the random sweeping hypothesis. Basically, the Doppler effect due to the mean air velocity broadens out the spectrum to achieve that frequency to the -5/3 dependence. And that's quite interesting, and there's some very good implications of that. But I want to talk in engineering terms about what we can learn from the frequency spectra behavior for grid integration. So let's take a look at the 20 largest wind plants in the US state of Texas. The insert shows Texas superimposed over Western Europe, so you can just see these plants are spread over a fairly large area. Here's the power spectrum of one of those wind plants, and you get that frequency to the -5/3 behavior. So the question is, what happens when we add some of these plants together? Does it smooth the fluctuations out? And the answer comes quickly. Here's 4 plants together, and we see that the high frequencies are somewhat damped, but not much change in the very strong low frequencies. Here's all 20 of the largest wind plants added together, and you get about an order of magnitude of smoothing at the highest frequencies and essentially none at the lowest frequencies. At periods like an hour, you actually damp out about 95% of all of the fluctuations, but at 12 hours, it's only half of the fluctuations, even adding all of the wind plants together. So I'll show you that quantitatively. What we've learned are 2 basic things about smoothing by geographic diversity from looking at the physics here. The first is when we talk about smoothing, the time scale is very important. As I mentioned, 12 hours has a whole lot less smoothing than an hour. 12 hours, we smooth about half of the fluctuations. At an hour, we smooth about 95% of the fluctuations. The second is the point of diminishing returns from connecting wind plants together is very quickly reached. You get almost to the asymptote after about a half a dozen wind plants are added together. So again, the top curve is the 12-hour, the strong fluctuations. The bottom curve is the smaller fluctuations, but important for the grid. And you smooth about 95% of that out. But that means that if you have a small scale, you can add just a few wind plants together and smooth much of that out if you're feeding, let's say, an electrolyzer or an ammonia plant. So what about solar? We know that the insolation curve is modulated by clouds, and you get these fast and deep fluctuations. We looked at 20 PV plants in the Indian state of Gujarat. That's a peninsula in western India. There it is in the insert compared to Germany. Again, it's not a small place. We looked at plants from 5 to 220 megawatts, and we found the same sort of power spectra, except there are a lot more harmonics of 24 hours, as you might expect for the power spectrum of PV. But again, the amount of smoothing achieved with 20 plants is about the same as you get with 10 plants. And let's compare the smoothing of PV to that of wind. And what you see on the left is the same curves I showed you for wind. And on the same scale on the right is PV. Instead of smoothing out 95% of the fluctuations at the asymptote with 20 plants, you smooth out about half. Instead of smoothing out 75% at 6 hours, you smooth maybe 25%. So the smoothing of PV, if you're feeding something like the electrolyzer or the ammonia plant that we were talking about earlier, is going to require much more compensation. Right. So what about solar thermal? We expect that the thermal inertia of the working fluid in a solar thermal plant will help smooth the fluctuations. This was the biggest solar thermal plant in the US at the time we published this. And again, we see that. The top two curves, the purple and the green, are a couple of different PV plants. The red one is a wind plant, and the blue one is the solar thermal plant, considerably smoother than even wind. So although we don't have a lot of solar thermal plants to add together, we expect that adding those together will achieve even more smoothing than we get for wind. So I teach in a business school. I ask the question of what's that cost? Using the ancillary service prices in California, we can say that integrating wind and solar thermal costs $4 or $5 per megawatt hour, and it's about double that to integrate solar PV. It's entirely achievable. Just because there's no free lunch doesn't mean you can't eat. It may be expensive. So back to wind, I want to just touch on one more aspect of wind that we've learned in this way. And that's, well, what if we add all of the 4 biggest wind-producing regions in the US together? Don't you get much more smoothing? And although I don't have time to go into the details here, the answer quickly is no. You don't get any more smoothing adding the whole country together than you get from just one region. And again, Mahesh Bandi, a wonderful fluid dynamicist, has found that the maximum possible smoothing, that is the steepest slope of that curve, is frequency to the -7/3. And what that means is even in continental scale, wind interconnection has limited benefits in smoothing the fluctuations. So I hope I've helped to convince you that looking at the basic physics and mathematics of some of renewable energy is important in helping us to achieve grid integration. These are some of the folks that have actually done the work, and so thank you very much.
Thank you, Jay, for showing the smoothing of wind fluctuation and PV's fluctuation. Now we come away, or we leave the fluctuations, we come to baseload and heat supply. Eva Schill, she will present the challenges of the geo-energy transition. Eva Schill is a geologist and holds a doctoral degree in geophysics. She is professor in Darmstadt and also in Karlsruhe at the KIT, and there she leads the geo-energy group. She leads the Helmholtz research infrastructures, 2 big projects, the Deep Store on heat storage and the GeoLab, an underground research laboratory to develop enhanced geothermal systems. Eva, it's your turn.
Yeah, thank you very much, Jutta. Before I start, I also would like to express my personal condolences and also the condolences of the whole entire KIT with our colleagues and friends in Israel. I would also like to point out that my presentation now focuses on heat, and you already see in the figure the campus of KIT, and I will also explain you why you see this picture. But on a global scale, of course, geothermal energy is much used also for electricity generation. And we have, for example, published in 2011 the IEA roadmap on geothermal, and this was entirely on electricity production. So why do we focus on heat in Germany? Because the electricity production is challenging at a low temperature, and we basically went one step back, and we are convinced that we first want to serve the heat market, and I'm also convinced that in a few years we will go back to electricity. So the situation in Germany, and I would like to give maybe a positive impulse of our politicians. We recently got a new law, the new building energy law, and one of the elements of this law is that all communities have to do a heat planning. And we already observe now that this has a very positive impact also on the geothermal development. Why this? We have a number of district heating networks in Germany, about 1,400. 14% of our buildings are heated through these networks. They are low temperature, 80 to 130 degrees. And the vision of Germany, of the German government, is that we will have 42% of the German buildings heated in future through district heating. This means, by the way, 100,000 new connections to district heating per year in the next years. So it's also a challenging number. The district heating should be to 30% climate neutral in 2030 and fully climate neutral in 2045. So how can geothermal energy as actually a baseload energy contribute to this? The current state, and this is for many countries, I think the same. In Germany, there are some countries that manage much better than we do, obviously. But in Germany, still 75% of the primary energy come from the geosphere. And also 75% of the heat come from fossil georesources. So that's why I also mentioned in my title the geoenergy transition. So we really need a geoenergy transition. On the other hand, we have identified a market potential from hydrothermal resources. So this is the current state of technology in Germany of 25%. That means we could actually cover 25% of the heat demand in Germany with the development, of course, by 2045. By the way, we speak about 300 terawatt hours, so we had this question yesterday already. We should talk about big numbers. I think this is a considerable number. I'm glad that you agree with this. The issue or the problem, the challenge is that this is heat which is located to specific areas in Germany. This is the pre-Alpine basin, it's the Upper Rhine Valley and the North German basin. But for these resources, we have a technology. So if we use geothermal baseload energy for heat, then of course we come directly into the discussion that we have a seasonal gap between the heat demand and what we can supply. The solution which we follow is that we look into large volume and high temperature heat storage. So high temperature would be above 140 degrees so that we can feed in about 110, 120 degrees into the district heating network. And the second challenge I already mentioned, we have a high site dependence for this technology, which we are currently using. And we want to go, of course, towards site independence. And there is a solution, a new technology, which is called EGS technology, which we follow since a few years already, but has some challenges that have to be overcome. If we talk about these two, or if we want to include these two technologies, then we can talk about 500 terawatt hours in 2045. Of course, we have to develop the technology. I want to bring you to the Upper Rhine Valley in southern Germany, and so you see it on the map. This is this graben structure, which is basically full of wells. These are unfortunately not geothermal wells, but former oil and gas wells. We have about 1,000 wells there. Most of them are not in operation anymore. But, of course, from these wells we have really good information, and we can basically now look at them and analyze if there are for storage. So if the fields are interesting for storage. And this brings us to the next challenge. When we did analyze this, we noticed that the way of in the reservoir has a big influence on the storage capacity, and you can see on the left side, when we engineer it with vertical wells, we have a rather distributed storage capacity, but if we use a horizontal well section, then you can that the storage capacity moves to higher storage capacity. So we also now look into new technologies that, of course, horizontal wells are not a challenge anymore, but they are a big challenge in this environment. Just to give you another number, for the storage capacity per Rhine Valley, if we only consider the oil fields, which we know, we would have a storage capacity of 10 terawatt hours per year, which is our number, and this is basically a minimum number. That's the challenge in this heat storage. What you see here is a section through a former oil. It's a very classic oil field. You have a gas on top, then you have the oil, and at the base you have water. The water in the reservoir has a very high salinity. You can see the values for chloride and natrium, I forgot. So it's about 120 gram salt per liter water. And you can imagine, or you can see what is the problem of this high salinity in the lower part. This is from the Pannonian Basin. As soon as you change temperature, you have precipitation and you get scaling, and so the challenge is really to find conditions that we do not have these scalings. So what is KIT doing? We are currently installing, and Jutta mentioned this already, a research structure on this high temperature storage with 2 wells. Within the next years, we want to solve these issues for high temperature heat storage so that we bring this technology to the market. This is indeed an experiment, so no one has ever gone to such high temperature storage. But we are already in discussion different utilities, and so we will implement, by developing the technology, also already implemented with different companies. One of them is Stadtwerke München. The other one is for BW and Stadtwerke Karlsruhe. So the second technology, which would give us site independence, is the ETS technology, and I think that the most famous part of geothermal, unfortunately, was that geothermal project caused induced seismicity past. We did this also in a prototype plant in France for EGS. And you just can see all these points which you can use events. You can also see the number located. Yeah, there are much more that happened. See that we produce a number of 10, 20, 30,000 events stimulation experiment. And some of them are not sensible, but some of them are come up quite sensible magnitude. So in this project, magnitude was 2.9, and at a depth of 5 kilometers, this is really, you can feel the earthquake. So what are we doing in this direction? We have developed protection schemes, how we can avoid induced seismicity. This is just one example from hydrofracturing experiments, and what you can see is you can see the pressure and the flow rate for the experiment. And you see this red dots, which are acoustics, because it's on a smaller scale. And I just would like to show you is that when we do conventional injection, how always been done, then you can see the number of events is quite, and it's distributed across the entire experiment. Whereas when we test new injection scheme, on the right side, you can see that acoustics appear only in the very last refrac experiment. And this tells us that with the end of injection, we can really mitigate seismicity. This is a process which is a scientific big which is ongoing, and we need some fundamental research to understand the hydrodynamic processes behind. And therefore, again, KIT, other Helmholtz institutions, is currently up underground laboratory, probably in Darmstadt, we hope. So what we're going to do in this underground laboratories, we want to really go into existing fractures as we have them in the thermal reservoirs, in the granite, and we want to do experiments with different schemes, different pressure differences, and so on, in order to understand the fundamental hydrodynamic process in this injection. And this is the last line. You can see we do this not alone. This also in particular together with our French, but also American colleagues from the DOE Forge project, Jutta, and the respective national labs, which are in this project. So we hope to tackle the challenges for the future. Thank you very much.
Thank you for the insights into the geoenergy transition. So what is missing within our session? We said that we have a last view on the photovoltaic, so we want to look at the sustainability. And this is Iris Visoly-Fisher. I see her there. Okay, morning. And she will present the talk with the title Stability and Sustainability Challenges of Next Generation Solar Cells. Iris is the head of the Solar Energy Center in Ben-Gurion University of the Negev, and her research focuses and is the stability of the photovoltaic materials and devices and the stability testing of emerging photovoltaic technologies. She is a member of the Israeli President's Climate Forum, Energy and Industry Cluster, and in the steering committee of the Energy and Sustainability Center. So the right person for now. Iris, it's your turn.
Hello, can you hear me? Can you please let me know if you can hear me? Okay, thank you very much. Thanks so much, Jutta, for the kind introduction. And thank you everyone for your kind words. If just a personal word, this is heartwarming to hear about your support. So as Jutta mentioned, I come from Ben-Gurion University, which is located in the southern part of Israel. This has very important two implications that are relevant to today's meeting. One is that we are within the missile range of Gaza Strip, and therefore, if there is bombing when I speak, we will have to stop, but I hope we've been relatively quiet over the last few days. And the other thing is that we are located in the desert. And this means that we have a lot of sun. Actually, Israel's area is between 1/3 to 1/2 is arid area that has very little rain, but has a lot of sun. And utilizing this source of energy as an asset to the country of Israel is something of national importance, and that lead to the establishment of the Solar Energy Center at Ben-Gurion University, which deals with multi-scale research. We look at the nanoscale, so we look at materials and nanostructures. We do research on the microscale, that is device and panel levels. And we also look at the macro scale as how to integrate different solar converting technologies together into the grid. I'm going to show you just a couple of examples of what we do today. But before showing that, I want to note that we are part of the Blaustein Institutes for Desert Research, and that has implications to the way that we do things. These institutes are an academic research institute, which includes people from very different disciplines, looking into utilizing the desert assets for the benefit of humanity, from solar energy to desert agriculture to water scarcity issues. In a sense, my talk is the party popper talk of this meeting, because on the left you can see how wonderful renewable energies are in terms of reducing greenhouse emissions, and especially when we talk about photovoltaics, they have very low greenhouse emission when it comes to generating electricity and energy. But less thought and less discussed is the environmental impact of photovoltaic technologies, which is what you can see on the right. And the environmental impacts are on almost every stage of the life cycle of photovoltaic systems, but also on every aspect of environmental ecosystems. There's resource consumption, and the limited resource and critical resourcing has been mentioned before. That applies to precursor materials, to producing and manufacturing photovoltaic systems, but also to land use. There's ecological impact, which implies mostly to the operation. You are affecting ecosystems on the ground because you're affecting the use of land, the albedo, the local temperature, and the local wildlife. And there's also the issue of pollutant emission, which applies mostly to disposal of photovoltaic systems at their end of life, but also to emission of toxic substances during the manufacture of photovoltaic systems. So putting all of this together implies that photovoltaics are very good when it comes to greenhouse emissions, and it's a good option and a very important one when it comes to the plans for limiting the climate changes and global temperature increase. But they do have their challenges that needs to be approached in terms of environmental issues. And I'm going to show you a couple of examples of research that we do in that sense. Professor Rech has so kindly introduced the topic of perovskites and how wonderful they are. And indeed, perovskites is a magic material that is very satisfying for a researcher to work with, because it's a very flexible material. So you can change the chemistry, and by that change much of the properties of the material. It's very easy to handle, so you can manufacture it using wet chemistry. It really is benchtop chemistry, and you get wonderful results. It is a very good semiconductor, which make high efficiency solar cells. It does have a couple of challenges associated with it. One is the presence of lead and tin as part of the high efficiency compositions of perovskite. And the other one is the issue of stability. What you can see is the relation between the lifetime, or T80 lifetime, which is a measure of the lifetime of photovoltaic solar cells or photovoltaic technologies, and their efficiency. This is where silicon is. This is the current commercial technology that most of us see and maybe use everywhere. And it has high efficiency and high stability. However, it also has high costs, both in terms of the monetary cost and in the environmental impact of the manufacturing cost. Furthermore, the energy input into manufacturing silicon cells is relatively high, and so the energy payback time is non-negligible. If you go to emerging technologies such as polymers and small molecules and dye-sensitized solar cells and perovskite, you go into much, much cheaper technologies, both in terms of money and in terms of energy and environmental impact. However, you either pay the price of low efficiency or you pay the price of low stability. So perovskite, in terms of efficiency, are a good competitor to the silicon technology. However, in terms of efficiency, it is still very limited. That is a problem from the environmental aspect, because, as we said before, limited lifetime would imply higher disposal rate. And not only higher disposal rate, but also higher manufacture rate, which consumes much more of the resources than we would really like to have at that technology. To address that challenge, we at Sodebo Care are utilizing our greatest asset, which is the natural sun that we have, to study stability, both to understand degradation mechanisms, but also to test different technologies to improve stability of perovskite solar cells. What you can see here is a comparison of our measured solar spectrum at noontime, which you can see that's the blue line. Sorry, these are the black dots or the black circles, which follow very closely the textbook spectrum that is used, the AM 1.5G, follows exactly that, showing a much better spectrum than a solar simulator, which is the red dots that you can see here. So we really use natural sunlight to test the stability of solar cells in condition as close as possible to outdoor conditions. We have setups for outdoor measurements of lab scale cells during research, academic research, and low scale research, and they experience the same conditions as a full-scale photovoltaic system would experience. However, we also take the solar light and introduce it into the lab. And what you can see here is a photo of a system like that. And without going too much into the details of it, you can see the collecting optical system outdoors, which transfers light through an optical fiber or through a set of mirrors into the lab, where we can do very well-controlled experiments using natural sunlight. Not only that, but we can also concentrate sunlight such that we can control not the spectrum, which remains the natural spectrum of sunlight, but also the intensity of sunlight. So we can multiply and use 1 sun or 2 suns or 3 suns or 10 suns or even more than that to do experiments in the lab under very controlled conditions. And we use that, and I'll just want to point out one example. We use that capability to understand the mechanism that govern bias-dependent degradation of perovskite solar cells. What you can see here are experiments where we tested the changes in efficiency and power conversion efficiency of perovskite solar cells as a function of dose. Dose is the intensity of sunlight multiplied by the time of irradiation. And what you can see is that when the cells are stated at open circuit, which is these conditions on the current voltage curve, all curves fall on roughly on the same line, even though the red ones were measured at 10 suns and the green ones were measured at 20 and 30 suns. So different light intensities, but really what counts is the dose. If you think about it and you consider which mechanisms can be affected by bias and are pointing out to or related to accumulated damage, then we can come to the point that charge carrier accumulation is an accumulated damage that contributes to defect and trap formation. This is probably the dominant degradation mechanism under these conditions. However, if you use short circuit, so these conditions, you see a very clear difference between the different illumination intensities, which means that in this case, the degradation rates depends on light intensity. That is the rate of causing damage and not the accumulated damage. If again, you want to consider that, this is probably photo-generated vacancies at the active layer that cause intralayer and interlayer massive ion migration that occurs and causes the cell degradation. This is just one example of how we can use natural sunlight for studies of stability of perovskite solar cells. Another aspect of that is that we can look at the differences between nighttime and daytime. Apparently, perovskites have a very unusual property where they change their efficiency as a function of time. What you can see here is measurements of the efficiency as a function of several hundreds hours outdoor, where we follow the efficiency as a function of time. This would be the days, and this would be the nights. And what you can see is the efficiency consistently increases during the day under illumination, and then decreases from here to here, or from here to here, or from here to here during the nighttime. These kind of reversible processes are very unique to the perovskite photovoltaic technology, and we have the power to test it because we can observe the differences between light cycles and dark cycles. To understand better the mechanisms that are correlated with that, we went on to doing some indoor light cycling experiments. And without going into the details, the biggest difference that we see between photovoltaic performance under light and during the dark cycles are in the short circuit current and the field factor, which probably means that there is some reversible mechanism that is correlated with charge collection that we can detect when we look at light cycling, first outdoors and then indoors, but you couldn't really even detect it if you just use the conventional constant illumination tests that are typically used to study stability. Another aspect, which I will just touch on very briefly, is the presence of toxic metals. Lead is, of course, very concerning. Tin is also not a very fun metal to work with. They are both very toxic. And if you calculate in the typical perovskite structure, there's about 0.4 grams per meter square, which is orders of magnitude larger than the acceptable limit of lead in electronic structure. Do you want to guess how much lead there is in silicon panels? Take a second. I hope you guessed right. It's more than an order of magnitude larger than the quantity of lead in perovskite solar cells, because there's always lead in the solder wires. If you look at the issue of lead globally, you would see that lead exists mostly in batteries. These are lead acid batteries that if you're not driving an electric car, you're probably using one of these. And that is responsible for about 85% of the lead in the world, such that even if we stopped using photovoltaics altogether or just perovskite, would probably make very little difference to the lead quantities used in the world. If you calculate the amount of lead that you would need to provide the entire electricity needs of the US in 1 year using perovskite solar cells with 25% efficiency, which is the record efficiency, and 30-year stability, which is yet to be achieved, it would require about 160 tons of lead per year, which is a lot of lead, but it is still an order of magnitude less than the lead that is currently used per year in all over electronic utilities in the US in the same time. However, this is a concern, and in this research, we took advantage of our very interdisciplinary background of the researchers in the Blaustein Institute for Desert Research, and we coupled with a soil desert agriculture expert to study transport of lead cations in the soil. And cutting a very, very long story short, what you can see in this graph is that the lead is always stuck between 1 to 2 centimeters from the surface level of the soil. It doesn't go anywhere beyond that. We've very thoroughly studied the properties of lead in soil, and we ran some further simulation to simulate what would happen if we had more and more rain and more water going in. And what you can see here is that even in the worst case scenario, depending on the type of soil and the amount of water, you get to about 6 centimeters below ground level, which effectively eliminates the danger that lead cations from perovskite will reach the groundwater. I could go on and tell you why is that. It's related to the structure of perovskite, but of course we're not going to go into that. So to summarize, I first want to point out what we still need to learn in terms of the environmental impact of photovoltaics. We need high efficiency and long lifetime new technologies, because these would reduce the quantities of manufacture and disposal. We need to study the environmental impact to understand how big are the threats that we imagine that there are. They may not be as large as we think. And of course, we need to plan in advance for circular economy of manufacture and disposal, such that when we get to the end of life of these photovoltaic systems, we could either recycle them or dispose of them safely. I've shown you that we can use natural sunlight to study different degradation mechanisms in order to understand how we can improve the stability of perovskite solar cells, and that we've done some soil transport studies to understand the risk of lead, which is probably not as big as we think it is. And by that, I want to thank you for your attention.
Eva, I haven't understood the new system which you explained. What is behind the technology, this EGS?
Yeah, so EGS, we call it Enhanced Geothermal System. It's a technology which we follow since 20 years, I would say, but it's still, we have only one prototype worldwide. So what we do is we use fractured reservoirs, so along faults, for example, tectonic faults, and the thermal water circulates in these fractures. And very often we do not have a good connection between the well and the fractures, or the hydraulic conductivity of the fracture system is not high enough to produce at economic viable condition. So what we do is we inject water, it's really comparable to the fracking process, but we do not frack the rock, but we basically shear, we hydro-shear the fracks, and then the two sides of the fracture do not fit to each other anymore, and we increase in this way the permeability of the rock. So this is the technology, and while you shear the rock, if you have a very high shear strength, you can produce induced seismicity. Normally you do it. It's very easy actually to produce induced seismicity. And the question now is how can we change the conditions in order to mitigate this induced seismicity. And one example I have shown that we changed the strategy. So in order to, or instead of massive injections, we have these stepwise injections, and then we basically slowly open and close the fracture, and then until it shears much slower. So it's always a question of velocity, basically. And when it shears slower, then it's an aseismic deformation, and we don't have this induced seismicity. So this is one possibility. The other possibilities, what we observe is that when we have hydrothermal alteration on the fracture, that means clay minerals on the fracture, then we have a natural reduction of the shear strength of the fault. And so this is also something what we actually want to develop in Darmstadt, that we basically inject clay nanoparticles into the fractures before we do this operation in order to reduce the shear strength of the rock. So it's really to increase the permeability in the subsurface.
So that what I understood is it is not so new. But will it be the only technology afterwards, or is it one of the technologies?
No, it's one of the technologies.
Okay.
So in the areas where we have favorable conditions, we don't need it. Yeah. So we have in the US or in Indonesia, we have volcanic areas. There we do not need it. But for example, in the US, where we follow this FORGE project now, we have even in the conventional areas, in the conventional geothermal sites, we have areas where we have dry wells. And this is the idea to make these, to connect these dry wells also to the field. Yeah.
Thank you.
Sorry for, I just want to say we should get to the closing of the session because we are a bit late. I know that I see that there are some comments, maybe very short ones, and then let's try to reconvene, let's say at 12:05 here again. We have some buffer time during lunch, but yeah, that's what I wanted to say. Sorry for interrupting.
Okay, then I saw 3 questions. So you.
Let me just make a question for the organizers. Are we going to be provided copies of the slides? Because there were many interesting references on people's slides.
Okay. Jay, I think the answer is yes. I asked about that earlier.
Okay,
and I'll be very brief now. Iris, I really liked your talk. If you've not found it, there is a National Academy report of a couple of years ago called The Hidden Cost of Energy, which goes through and systematically applies dollar values on the externalities of various energy systems. You started with a more elaborate description of some of the externalities associated with solar PV. You might take a look at that report and see if there's something in terms of valuing the externalities associated with the production of PV is something that you or one of your students might undertake.
Thank you very much.
Okay.
I just want to add just a short comment on the problem with the lead. Yeah? So I totally agree that the amount of lead is really not of a major concern. Nevertheless, the European Union has lead on its ban list, and for the batteries, every 5 years it is now evaluated if there are alternatives or not. And even though the lead-acid batteries have 99% of recycling quotas, and there's no emission in operation, and around the factories you will not find any lead emissions. Yeah? So I think this is something we have to point out maybe from science much more, that some of these bans of materials are beyond realities, I would say. Yeah? So, for the perovskites is maybe one of the essential points.
Thank you. That's a very important comment. I just want to add to what you said is that the European Union has exempt photovoltaics from the lead constraints. Probably because of the very common use of silicon panels, which contain a lot of lead. But everything that we know about lead constraints, it is true. It doesn't hold for photovoltaics. So just to tell you a funny story, I've had this company who wanted me to work with them on developing perovskite solar cells, but they said, oh, it's going to be a very short-term research because it has lead and it will never commercialize. We were working on this literature review, and a couple of weeks later, I just sent them the sentence that says that photovoltaics are exempt in the EU, and a couple of weeks later, I got a 3-year contract on that research. So always check the literature, the fine prints.
Yeah, I have a question to Jay. So, yeah, here. Thanks very much for the talk. I would be interested, have you looked into whether you can further smoothen the volatility by combining wind and solar?
Yeah, we have looked at that, and actually it turns out a little surprising to me. It's pretty much a linear admixture. Now, having said that, getting wind data and solar data co-located was very difficult. The wind and solar operators tend to protect their data in ways that, as a scientist, I consider irrational. But basically, yeah, when you combine them, it's just a linear admixture. But an interesting question.
Okay, thank you for the presentations. Thank you for the questions and the discussions, and we can close the first session. Thank you.